All right, here's the 9.9 webassign representing functions as a power series, number 4 and 5. Now, these are a little bit different from 1 to 3. You can pretty much immediately see why. We're trying to represent this power series right here. So that's really what the question is. They do give you some nice information here. They say this power series can be represented like this, and that's we could do that pretty simply. We would just change this into the sum of a geometric series, but they already did it for us. But it gets more complicated than that. They're saying we want to figure out what the power series for this function is, given that this is the second derivative of this function. So what does this have to do with this? Well, we know the second derivative of this is what we're looking for. And by the way, the second derivative of this, I'm saying the second derivative of this is what we're looking for. But this looks a lot like what they gave us. As a matter of fact, if you factor out a 4 from your derivative, it's exactly what they gave us. So, remember, you can take derivatives and integrals of power series and just basically normally. So, if we can take the second derivative of the power series of this, which is given, we'll have it. So let's do it. So we're going to take the second derivative of this whole power series. Negative 1 to the n is going to be a constant. We're doing this with respect to x, remember? So here we go. The first derivative of this would be negative 1 times n to the x to the n minus 1. The second derivative would be n times n minus 1 times x to the n minus 2. So we just brought this down again and subtracted 2, and then we have a 4. So we've done it. Now, the one thing here is this. If we leave this as n equals 0 to infinity, now we're dealing with 0 and a negative 1 and 1 and 0. So we really have to start this at 2. But we can back that up. We can, and if you're looking at their answer, we can back that up to 0 as long as we start raising these n's by 1 each time. Think about that. So if I want to start this at 0 instead, I'm really going to use the n plus second term. I'm going to start with the n plus second term from this. So I would really have negative 1 to the n plus 2 times n plus 2 times m plus 1 to the x to the f. And that would be an equivalent series, and that would be a better written series. And you can see that that's where that answer is from. But if you just wrote this answer, that would be legitimate. Just make sure you're starting at 2. Now, the interval of convergence. We also learned that if you're integrating or differentiating a power series, the interval of convergence doesn't change, but the endpoints may change. So the interval of convergence for this is x's between negative 1 and 1, not including negative 1 and 1. So the interval may change, so you need to plug in the endpoints to this series right here to see what happens. And if you plug -1 in for this x and then +1 in for this x, you're going to see that this series is definitely going to diverge. It looks like from the nth term test. So you still don't include those endpoints. That's what the interval convergence of this would be. Think about that as well. Sometimes this you kind of have to absorb all this information, and it takes some time. But let's go to the last one. Last one is very similar. They gave us the similar power series as before, but they want us to figure out the power series for this, the natural log of x plus 1. But we're given that, that natural log of x plus 1 is the same thing as the integral of 1 over x plus 1. So if we want to get a power series for the natural log of x plus 1, all we need to do is integrate the power series for 1 over x plus 1, which is given here. So let's do it. If you're integrating -1 to the n times x to the n, you will get -1 to the n is a constant. We're integrating with respect to x. Add 1 to the exponent, divide by n plus 1, and that's our power series for the natural log of x plus 1. Plus c. Almost forgot. That's annoying. The plus c is always annoying. So let's use an initial condition. Center at 0. We know that if you plug in 0 for x, you get the natural log of 1, which is 0. So if you plug in 0 for this x, this power series would be, since it's the natural log of x plus 1, would be 0. So we get 0 equals c plus 0, so c equals 0. So therefore, we can eliminate that c. We're not really eliminating it, it just equals 0. Interval of convergence. Now, this is different from the last one we just did because that the n plus 1 here is on the bottom. So we won't always have a divergence by the nth term test. So the right m, we see that the interval of convergence of this function is -1 to 1. So the left endpoint, because when you integrate a function, a series, it will have the same interval of convergence as the original series, except maybe at the endpoints. So that's why we're going to check the left endpoint, which is -1, into this series. So we have summation of -1 to the n times -1 to the n plus 1 all over n plus 1. Now, -1 to the n times -1 to the n plus 1, those are guaranteed to be opposite signs. So you're always going to have -1 over n plus 1 on this, and that is definitely going to be a divergent series if you just compare it to 1 over n. So we should not include the left endpoint. For the right endpoint, we're going to plug in 1. So x to the n plus 1 is 1. Now this is a alternating series, and by the alternating series test, the limit of a sub n will go to 0, and a sub n plus 1 is always less than a sub n. The alternating series test says this converges. Therefore, our interval of convergence for this series that we found would be from -1, not including it, to 1 inclusive. So there you go. And that was it for the WebAssign.